right, let's get right into it. Ever wonder why, even with all our amazing tech, stuff still breaks? You get something brand new and there's that one tiny annoying flaw. Well, it all goes back to this epic battle that's happening right now on factory floors, a battle against imperfection. And today, we're going to break down how that fight is being won using a pretty killer combo of old school stats and brand new AI. So, everything starts out perfect, right? It begins in the digital world, as a flawless blueprint or a perfect 3D model. I mean, in a perfect universe, every single part that comes off the line would be an exact copy of that design. A perfect match every single time. The thing is, we don't live in that universe. Because, let's be real, that's just not how it works. The factory floor is all about tiny errors, scrap bins full of bad parts, and super expensive rework. So if the design is perfect, what gives? Where does this huge gap between the blueprint and the final product come from? What is this invisible force messing everything up? Well, that enemy has a name, and it's called variation. It's this sneaky, natural wobble that finds its way into every physical process you can think of. I mean, even the most advanced, high-tech machine isn't 100% consistent. And all those tiny little inconsistencies, they add up. They become big, big problems. So if you want to beat it, you first have to understand it.
Okay, so engineers have a really smart way of breaking this down. They see two types of variation. First, you've got common cause. Think of this as the normal background hum of the factory. The tiny vibrations, the slight changes in temperature, it's just part of the process. But then there's special cause variation. And that's not a hum, that's a siren blaring. It's a huge red flag that something specific just went wrong. A tool wore out, an operator made a mistake, and you need to figure it out right now.
So the big question is, how do you actually tell the difference between the background noise and a real alarm? For decades, the secret weapon has been a really powerful set of statistical tools. And this, my friends, is where the real detective work kicks in.
It's called Statistical Process Control, or SPC for short. And you can pretty much think of it like a doctor's stethoscope for the entire manufacturing line. Instead of just waiting for the patient to get really sick or, for a pile of bad parts to show up, SPC lets you listen for the very first faint signs of trouble. It's all about catching problems early so operators can step in before things get really bad.
And to do that listening, operators use this classic playbook known as the Western Electric Rules. Let's quickly run through the big four. Rule 1 is the big one, the no-brainer. If you get even one single measurement that's way, way outside the normal range, what the pros call the 3 sigma limit, that's it. It's a fire alarm. You drop everything and find out what just happened. Okay, rule 2 gets a little more subtle. See, one bad point could just be a fluke, right? But when you see 2 out of 3 points in a row drifting into that warning zone, that's different. That's a pattern. And it's telling you your process is starting to wander off course. Then we have rule 3, and here the signal gets even quieter. Now we're looking for 4 out of 5 points in a row that are starting to creep to one side of the average. Any one of those points by itself means nothing. But you put them together and they're painting a really clear picture. Your whole process average is shifting and you're headed for trouble. And last but not least, rule 4. I love this one. It's so clever. It's designed to catch those small, sneaky problems that just hang around. If you get 8 points in a row that are all on the same side of the average, even if they're all technically good parts, that tells you something fundamental has changed. Your process just isn't centered anymore. And look, this isn't just some abstract textbook theory. This awesome quote from an engineer on Reddit just nails it. This stuff is used on the floor every single day. It's almost like a secret code. An operator can just glance at 2 numbers, CP, which is kind of like the machine's best case potential, and CPK, which is how it's actually performing right now, and they know instantly, is this something I can fix with a quick tweak, or do I need to call an engineer because something is seriously wrong with the process itself? Okay, so the alarm's gone off. SPC is great at telling you that you have a problem, but the real multi-million-dollar question is, why? This is where the engineers put on their detective hats, and luckily, they've got some classic tools to help them crack the case. One of the most famous is the Ishikawa diagram, but pretty much everyone calls it a fishbone diagram because, well, it looks like one. It's a super organized way to brainstorm. You put the problem at the head of the fish, and then the bones are all the possible causes, broken down into categories. Was it the machine, the method, the materials, the person, or man, as they call it? It helps you think of everything. And this whole investigation, it's not just random guessing. It follows a really strict, powerful cycle called DMAIC. First, you define the problem clearly. Then you measure it with hard data. Then you analyze that data to find the true root cause. Next, you improve the process. And finally, and this is key, you put controls in place to lock in those gains and make sure the problem doesn't creep back in. It's this non-stop loop of getting better and better. But here's the thing. All of that is about reacting to problems that have already started. What if you could see them coming? What if you could predict a failure before it even happens? Well, this is where modern data and AI are totally changing the game. We're moving from being reactive to being predictive. Just look at this graph. This is showing the force on a cutting tool moment by moment. See the first 20 seconds? Everything's nice and smooth, exactly what you want to see. But then, look what happens. The signal gets all choppy and noisy. Now, to you and me, that might just look like a little bit of static. But to an AI, that's a massive blinking warning light. It's the signature of a tool that's starting to fail, way before it breaks and scraps a super expensive part. So what does this actually mean in the real world? Is this just a cool science project? No way. In one study on making crankshafts, using this predictive approach cut down on bad parts and rework by, get this, 99%. 99. I mean, just think about that. That's practically zero waste. It means lower costs, way better products, and it's so much more sustainable. That's not just a small improvement, that's a complete revolution. So this brings us to what's next. And spoiler alert, it's not about robots taking over everyone's jobs. The real future is about creating these incredible human AI teams, where intelligent systems work right alongside the experts, blending the best of what machines can do with the best of what people can do. Yeah, this diagram looks a little complicated, I know, but the idea behind it is actually genius. What you're seeing is a system that brings two things together. On one side, you've got all this raw data from sensors getting crunched by a powerful machine learning algorithm. On the other side, and this is so important, you have all the wisdom and experience of the human experts captured in something called a knowledge graph. Think of it as the factory's digital brain. The AI gets to learn from both the numbers and the people. What this creates is this amazing feedback loop. The AI might spot something weird in the data and say, hey, you should probably look at this. The human expert can then check it out and say, yep, that's a real problem, or nah, that's just a false alarm. And every time that happens, the system learns. It gets smarter. It gets more accurate. It literally becomes a true partner for the engineering team. And this quote from the researchers who built this system just says it all perfectly. The point of all this isn't to replace the experts. It's to give them superpowers. It's about taking their incredible intuition and know-how and boosting it with the raw power of AI. The key is to put the human back in the loop, but it's a smarter, more powerful loop than we've ever had before. So that leaves us with a really big question, doesn't it? We've seen the journey, from just reacting to bad parts to predicting them before they happen, and now to actually collaborating with AI to stop them entirely. As our factories keep evolving into these truly intelligent partners, what's the next frontier? What's the next massive challenge that this human-AI partnership is going to help us solve?